welcome back to our course on drone surveying. In today's lecture, we are going to focus on the various softwares to process drone data. So, as you know, when we are trying to process the drone data, there are three major stages. There is flight planning and data capture stage, there is data pre-processing stage, and there is data processing stage, by the end of which we get our 2D orthomosaic or digital surface model. So, in the flight planning stage, we design the flight plans for automated data capture, and in this process we ensure that we have sufficient ground spacing distance, there is sufficient overlap and side lap, there is also good coverage of ground control points for photogrammetry. Then based on the flight planning, RGB, multispectral or thermal images can be collected. Once these images are collected, then based on the GPS track or GNSS track of the drone, the images are geotagged. Apart from that, images may also be cleaned, maybe some noisy images or some blurry images, they may be removed. Once we have the geotagged images, then we go for generating a sparse point cloud. Then this sparse point cloud, because it has only relative orientation, we integrate this with the ground control points for georeferencing. Then we generate a dense cloud point, and after that we go for orthorectification and generate 2D orthomosaic as well as DSMs and DEM. So let's look at the softwares which we can use in these different stages, and what are the open source softwares, what are the commercial softwares which are available to help us perform these processings. So let's look at the first stage, which is about flight planning and data capture workflow. So here we need to define what is the region of interest as well as the geofence. At the same time, we also need to define what UAV we have with us and what is the camera parameters we have available with us. Then based on that, we give the flying height, camera focal length, based on which the software calculates the GSD. We also provide image overlap. We also provide the camera angle and location of maybe GCP sites. Based on this, the software will generate the waypoints for survey grid pattern. Then we also provide flying velocity based on the wind velocity. And all this is then used for pre-flight simulation. Once we are satisfied with the simulation, then we deploy it into the drone using a ground control software. So there are majorly two different streams to go about it. There is open source way, which helps us in the waypoint grid planning, helps us in specifying the spots for camera triggering, also known as exposure stations, and also gives us option of executing features like terrain following. So the popular open source softwares are Mission Planner, provided by the company ArdioPilot. It has very wide compatibility and it has good flexibility with open source drones. So if you're creating your own drone, then Mission Planner is one good software that you can use to plan a flight with a drone which is developed by you. Also, we have QGroundControl by PX4. Apart from that, we have commercial softwares, commercial ground control softwares. These are often provided by the drone manufacturers themselves. So they work as flight planning tools which are bundled with their hardware for seamless integration. They provide optimized performance, and they also provide survey specific features like high precision mapping. Although these are logged in ecosystem, they ensure reliability, but at the same time they also limit hardware flexibility. So software which is provided by a drone company A may not be useful for another drone company B. So these is a list of the commercial softwares which are currently available. Popular ones from the Indian manufacturers are Bluefire by the company IdeaForge, and it can be used with IdeaForge drones. There's another software called Insight, which is compatible with the drones provided by Arav Unmanned Systems. There's also software for flight planning called Skylark Drones platform, provided by the Skylark drones. And then there are international softwares like DJI Pilot, provided by DJI, Cubase 3D. There's also SenseFly eMotion, and then there's also Pix4D Capture Pro. Although Pix4D by itself does not develop any drones, it provides this software for various DJI and Parrot manufactured drones. So let's look at the process of using Mission Planner. So first of all, when we open the screen for Mission Planner, we can see on the top left corner, we can see various telemetry parameters. For example, we can see what is the altitude of the drone, what is the ground speed of the drone, what is distance to a waypoint, what is the yaw, what is vertical speed, and what is distance to the communication box. So as right now there is no drone which is present in this system right now. So all these values are 0. However, we will look at a simulation later on and then we will see how these values change when the drone flight takes place. Then second step is we have to specify which type of drone we are going to use. So is it a plane, or by that we mean is it a fixed wing or is it a multi-rotor drone? Then we also have option to establish a communication with the drone using different protocol. For example, TCP is one popular protocol for communicating with different devices. After that, we move to this plan button, over where we can specify the polygon within which we want to do the survey. So basically this is the region of interest. So we draw a polygon. We can also upload a polygon. After we draw the polygon, so these are the 4 corners of the polygon, and we also specify the home point. Home point is the point from where the drone will take off. Then we specify, or we right click and we specify the waypoints automatically. And for usual cases when the area does not have too much undulation, or does not have too many tall buildings, then we go for a regular survey grid. So we will look at that inside in subsequent options. So we click on auto waypoint, or given as auto WP, and then click on survey grid. Now this opens lot of options. The first option that we have to select and specify is the type of camera we have. So in this case, the camera we have is a Canon camera. So we have specified that. Usually these softwares have a full list of major camera models which are manufactured by major companies. After that, we specify the altitude, or the height above the ground level at which the drone is going to fly. So in this case, it is given as 100 meter. Then we specify the location of the camera. So camera is top facing forward. Then we specify the flying speed, which we are giving as 10 meter per second. So this depends on the drone that you have. So this is the speed we are going to use for this mission. We also ask the software to add takeoff and land waypoints. And finally, when the survey is complete, then we ask the software to specify the flight path in such a way that drone returns to the launch, RTL. That's it. So we check that, or we tick that option. Next set of options we have is about specifying the grid options. So primarily we have to specify the overlap and side lap. So as we have studied in previous lectures, then that minimum overlap of 60% is ensured and a minimum side lap of 40% is ensured. So in this case, we have given 75% and 60% respectively to be on a safer side. After this, we also have option of camera configuration, where we specify which lens we are using with the camera. So the lens that we are using, its focal length is 5 mm. It's a very wide angle lens. Apart from this, we specify the image width and height. Basically, what is the megapixel, what is the size of the image that we are going to collect with the camera. And we also specify the sensor width and height. So usually sensor width and height is updated automatically with the camera options. But if you have some other camera that you're using, which is not the model for which is not already present, then we can also specify the sensor width and height. Once we give all these options, then it calculates by itself the ground spacing distance. So in this case, based on all these parameters given by us, the ground spacing distance comes out to be 3.08 centimeter per pixel. Then you may also notice there is another option of specifying the angle here, which means the angle of the flight line. So as we already learned in a previous lecture that we should fly crosswind. So if we have already some information about the wind direction, then based on that we can specify the camera. So based on that we can specify the flight angle. So this is showing two different flight paths depending on the flight line which we have specified. So in this case we have 0° flight line angle. So with respect to north, it makes the flight path will make 0°. In this case we have 272° specified as the flight line angle. So it makes approximately 272 2°. So all the lines are in the direction of 272°, either along 272° or 180° minus 272°. So based on the wind conditions, the advantage of specifying these angle is that it will result in stable and consistent path. Then we look further. We can also look into the behavior of every waypoint which has been established. So we can look at every points which are established along the flight path. So some points will be labeled as waypoint, some points will be labeled as camera triggering spots. So waypoints are the start and end point of every flight line. Then in between those flight lines, we will have lot of spots where the camera triggering will take place. Let's say we don't want to trigger at every location, then we can manually select and change that behavior. Let's say we also want the drone to hover at certain point, or we want the drone to loiter at certain point, then also we can specify this using the drop down menu over here. Also, we have the option to specify the flying height of the drone, whether we want the drone to maintain a relative flying height with respect to the location from where it was launched. So in this case, it is maintaining a flying height of 100 meters with respect to the ground from where it was launched. Also, if we have very highly undulating terrain, then it is a good idea to use a preloaded terrain dataset. For example, you can use SRTM digital terrain model. Then advantage of using a digital terrain model, or if there are trees and you have very good digital surface model, then advantage of using either a DTM or a DSM, in short either a DEM, is that you can prevent the drone from colliding into some mountain, or you can prevent the drone from colliding into some very large stone, very large hill outcrop. So that option is also there, and this is known as terrain following feature. Then finally, this is the flight plan which comes as a result of all the parameters which have been given by us in the mission planner software. So here you can see the home, then the drone will take off from the home. It will go to waypoint number 2, it will follow this flight path, it will go here, it will follow the flight path, then from this location it will come here to the next waypoint, again go to the next waypoint like this, then go to the next waypoint, and in this way it will keep on following subsequent waypoints. It will keep on following the subsequent waypoints, and when the survey is completed over here, then it will, depending on the behavior we have specified, either it will return to the launch, or it may go to some other rally point, depending on how we have specified the behavior. Also, at this stage, it is a good idea to look at the number of overlapping photographs which are present at every point. For example, our region of interest is given by this red boundary, the outer red boundary, and we can see that inside that red boundary, almost every spot has more than 2 photographs. So number of photograph is shown by these spots over here. So if you have any spot which is only showing in purple color, that means it has only 1 photograph which is covering that. On the other hand, if you have spots which are showing red color, that means you have 7 or even 8 photographs which are covering that particular spot. So you can see all the outer edges, they have 1 or maybe only maximum 2 overlaps. However, all the inner edges, all the inside of this region of interest, every spot is being covered by multiple overlaps of photographs. Finally, it also provides us some kind of a summary of the flight plan, that in all, an area of 85,215 square meter will be covered. A distance of 2.43 kilometer will be traveled. Distance between consecutive images will be 23.1 meter. Ground resolution or ground spacing distance is going to be 3.08 centimeter. Number of photographs that will be taken is going to be 78. Number of strips will be 6. Footprint of every photograph on ground will be 123.2 by 92.4 meters. Distance between the lines will be 49.28 meters. It also calculates the flight time based on the velocity that we have provided. So this flight will last for 5 minutes and 4 seconds, which is sufficient for most drones because battery life in most drones is around 25 to 30 minutes, and it will take a photograph every 2.31 seconds. turn diameter will be 20 meters, and ground elevation throughout this flight will be between 266 to 277 meters above the mean sea level. So once we are satisfied with this, we can export this to the drone. We can also perform a simulation before exporting to the drone. So in the simulation, the drone is taking from this place and then it will fly along the waypoints. And after the simulation, if we are satisfied that the flight is taking place in the desired manner, then we can connect or we can load this flight plan into the drone. So let's look at the simulation. So during the simulation, you will see the telemetry parameters also change, and you can see that drone goes from one waypoint to another waypoint. And then drone comes back to the home location. So this was all about simulation. This was all about the mission planning of flight plan. Now let's look into the geotagging of drone images. So when we talk about geotagging of drone images, we need to have overlapping images, of course. We also need to have the drone observation log in Rhinex format. We also need to have a base of observation log in the Rhinex format. Sometimes there are other formats also used. For example, UBX files are also used, but essentially most popular formats are Rhinex format. Then based on the drone, which acts as a rover essentially, so based on the drone and the base observation logs, then we can generate precise coordinates of the image timestamp. Once we have the precise coordinates of the image timestamp, then we combine these with the images to generate geotagged images. Although this stage is not required in case of the RTK drones, because in RTK drones, the drone location itself is very quite accurate. So the photographs are geotagged very well. However, sometimes even in case of the RTK drone, it is not possible to maintain RTK connection. For example, if during any flight path segment, the GNSS signal was lost, then some photos will be taken in single solution. So their coordinates will not be very accurate compared to other coordinates of other photographs. So it's always a good idea, whether you have RTK drone or whether you have single positioning drone, to always go for correction using a base station which you have established. So essentially, in order to geotag drone images, we need GNSS data from the base, from the drone, and also navigation file, which may be present either in the base or in the drone. And this navigation file is important because it contains the broadcast ephemeris data, which includes the satellite positions, it includes orbital parameters, velocity of satellites, clock correction, health status of satellites, and the timing information. So basically we load in the softwares the base information as well as the rover information. And also we need drone acquired images. So these drone acquired images, which have to be overlapping, of course. So these drone acquired images may be geotagged or they may not be geotagged, but it is always a good idea to again geotag them with the help of both base and the drone. So in this case, we are using an open source software called Emlid Studio to geotag the drone images. So first step that we do is we select drone data processing in the Emlid Studio software. After that, we provide the drone GNSS data. It can be in uBlocks or the Rhinex format. We also provide the base GNSS data in the uBlocks or Rhinex format, and we provide the navigation file in the Rhinex format. Once we give all these, then we also have option of specifying the antenna height of the base. So for the base, we specify the antenna height. For the drone, of course, the antenna height is 0 because antenna is on the drone itself. Then based on that, once we click process, then we can get the correct position of all the spots at which the images were collected. So these are the corrected locations or corrected coordinates of the drone at which the images were taken, or the corrected coordinates of the exposure station. Once we have the corrected coordinates, then we are done with the step 1. Then we go to second step, which is about geotagging. So we have the data, we provide the data of the timestamp, which is at each and every time at which the image was acquired. We also provide corresponding image name, so which image was acquired at what time, and then based on the corrected GNSS track of the drone, each of these images are geotagged. So after this, when we right click any image, then we will see in the image properties that now they have latitude, longitude and altitude information. So these are very useful in the photogrammetry in the subsequent steps. So in the final step, we will talk about how we can go from geotagged overlapping images to georeference dense point cloud, and from the georeference dense point cloud, how we can go from DSM to orthophoto. So such softwares will take in, or as an input they will take in overlapping geotagged images. Then they will perform first of all detection of key points, then they will match corresponding key points in overlapping photographs, they will filter out not so good key points, and then they will do the orientation of these images, relative orientation of these images. Once the relative orientation of these images has been done, then either using the ground control point or either using the geotagged informations already present in those images, the software will generate a georeferenced but sparse point cloud. Then the sparse point cloud goes further densification to give a georeference dense point cloud, which is then with the help of filtering algorithms used to generate digital surface model and digital terrain model, based on which the orthophoto and orthomosaic can be generated. So usually steps from the key point detection to sparse point cloud generation, these are performed in a single step in most softwares. It is followed by specifying the ground control point for georeferencing the sparse point cloud, and this is followed by densifying the point cloud to result in a georeference dense point cloud. So here the main deliverables that we expect from such softwares are orthomosaic, digital elevation model, 3D models, and also point cloud. And we can do analysis in the form of volume calculations and terrain mapping. We can also after that export to GIS softwares, for example, for use in QGIS or ArcGIS, or we can also export as object file to be used in the CAD softwares. And the role of software here is that it automates the structure from motion, it automates the meshing, it automates the ortho rectification. It enhances the accuracy. It helps us achieve centimeter to sub-centimeter precision with RTK and GCP workflows. It also enables scalability. It can process from 500 to 50,000 images via either GPU or through cloud. It also facilitates interoperability by supporting open formats like GeoTIFF, object.las. It also provides tools for quality assurance, for example, through point cloud editing, measurement validation, and report generation. So again, here also we have primarily two domains of either open source softwares and commercial softwares. In open source softwares, there is no or very minimal licensing cost. There is full workflow control. So which is very good if you're doing experimentation, you want to use it for research, you want to use it for teaching, or you have very limited budget for your project. It provides open code base, so you can understand each and every process by looking into the back-end code. It sometimes also requires more technical setup as well. And one limitation is that it may have fewer enterprise integrations. So these softwares are not integrated through a chain of other softwares, and they are often less optimized for large data sets and may lack some survey grade report. So we look into these open source software. Popular ones are RealityScan. There is also WebODM, which is built on Open Drone Map. There is CoalMap. There is also Meshroom. Then on the other end, we have commercial softwares which provide end-to-end workflows. They provide proprietary algorithms which perform often better than what present in the open source softwares. They have good documentation and support. They have survey grade accuracy. They have easy to use graphic user interface. Some softwares are now also providing cloud platform based processing. So even if you do not have a good GPU enabled computer, you can upload your images into the cloud and do the processing there itself. And therefore they are very useful, or they're becoming very useful for large volume processing and professional deliverables. So some of the popular commercial softwares for photogrammetry and drone mapping are Pix4D Mapper, there's Agisoft Metashape, there's ARDAS Imagine UAV, there's ArcGIS drone mapping, and Trimble Business Center aerial photogrammetry. So let's look into the open source software first. So while most other open source softwares are more focused on structure from motion 3D reconstruction, RealityScan is a bit different in the sense that it provides complete end-to-end workflow for georeference DSM and orthomosaic product generation. So RealityScan, it combines inputs from photographs and laser scan and supports highly accurate 3D mesh and point cloud generation. And it has also option of scriptable workflow. So you can control it through some Python scripts as well. And it can produce orthophotos, DSM textured meshes, and detailed virtual models for surveying, mapping, and also gaming and heritage documentation. It can perform georeferencing, automatic camera calibration, and coordinate system conversion. And one good feature of RealityScan is that it has fast linear processing. So if you double the input size, the processing time is only doubled. So it reduces weight for large data set, and it has low hardware demands. So even on a laptop, you can run a RealityScan with just a very 2 GB RAM also, 2 GB GPU RAM also, you can run RealityScan. As regards its licensing model, it is completely free to use for academics and for businesses with less than $1 million annual revenue. So let's look at general setup of RealityScan. So basically there are 4 major steps in RealityScan. First is adding the imagery. After that, importing other metadatas like control points or ground control points. Then second step is processing, which starts with aligning the images, calculating the model, texturizing, colorizing, and generating digital surface models and orthoprojection. And finally, it is about output, where we export these generated results in different formats. We can also perform application and analysis. For example, we can do volume calculation and area calculation. So first step is adding the images. So in our case, we have, as an example, we have added 634 geotagged images, and we also set the coordinate system to WGS84. After adding the images, it shows the location of every image, and you can see it aligns very well with the flight path that I showed you in a previous slide. Then we go for the step of processing and aligning the images, based on which it generates a sparse point cloud. So this is a sparse point cloud which is generated after image alignment. We can make out some features, but it's not as dense to be used as an orthomosaic map, or not as dense to be used as a digital surface model. Then by including ground control points and by densifying, we can generate dense point cloud. So we include also ground control points. So these are 5 ground control points which we have included in our example. Then visually we connect. So let's say this is GCP number 1. Then we find out in which all images this particular GCP is present. So for example, this is GCP number 1 and it is present in maybe 5 images. Then in those 5 images, we mark out the center of this GCP, right? This is what we do manually, and as a text, we have already provided the correct coordinates of the GCP. Then the software, then we repeat this step for several more GCPs. Then the software uses this to georeference and uses this to further refine the image alignment. Based on the refined image and based on the georeferenced image, followed by densification, then we have a dense point cloud from which we can generate a digital surface model. So this digital surface model is more useful to be used as a map in subsequent application. From the digital surface model, we generate the orthomosaic map. Then there is another open source software called WebODM, which is built on top of Open Drone Map software. This software WebODM, it is designed for both offline, desktop as well as scalable cluster deployment. It has GPU acceleration available for faster processing on compatible NVIDIA hardware. It can also handle split merge for large data set on resource limited systems. So let's say you have 10 square kilometer area, you can split it into 1 square kilometer area and then combine them and merge them later on. It is also fully scriptable via Python SDK and has a robust REST API for integration. So this is the layout of Open Drone Map. So right now I'm just directly showing the result of a sparse point cloud which is present, and based on that we can also generate a orthomosaic map here. After that, let's see some examples of commercial softwares. So most notable software among them is Pix4D and Agisoft Metashape. So commercial drone software provide streamlined workflows and are engineered for large scale, high precision photogrammetry and geospatial analysis. They provide robust support and regular updates. It is possible to achieve sub-centimeter accuracy via RTK or PPK and ground control point integration. They are particularly useful for leveraging GPU acceleration as well as cloud scalability for datasets exceeding 10,000 images, which corresponds to even 40 square kilometer area. So they are stable with large image datasets as well. Another feature of most commercial software is that they incorporate AI-driven features for automated feature detection and multispectral analysis. So looking at Pix4D Mapper and Agisoft Metashape, both are very popular commercial software and they deliver sub-centimeter precision for surveying, construction and agriculture with whenever we have RTK drone and sufficient spread of ground control points. They support RGB, multispectral, thermal, also fisheye and 360-degree cameras. They provide automatic aerial triangulation and camera calibration. They also have built-in tools for quality reporting, measurement, and radiometric correction. And one good thing is that they have both of these softwares. They have rich documentation and support, and they support advanced outputs in the form of DSM, DEM, orthomosaics, 3D meshes, geotiff, .las or .obj format. So this is the layout of a Pix4D mapper software where we have imported the images over here. So 68 images have been imported. Camera model has been selected. Coordinate system has been set as WGS84. Then based on that, we have option about which type of model to generate. Do we want standard 3D map? Do we want a low resolution but rapidly want to generate a 3D map, which is very useful in a field. So in a field, if you're doing the drone survey in front of you, it is always a good practice to have a rapid generation of digital surface model in front of you so that you are sure about that the survey is taking place as you expected. So even if it is a low resolution, but having a rapid map is very useful. Then outputs that we want to generate, whether it's orthomosaic or digital surface model. So we can all select that. Then these are the results from Pix4D Mapper. This is the image alignment, there is point cloud, there is orthomosaic. Similarly, we have Agisoft Metashape, where images can be imported and images can be aligned and models can be built on top of that. So again, we have option of the DEM and orthomosaic and point cloud. We can also look into the different type points. So one good thing is by looking into the type point, we can identify if there is any incorrect matching that may have taken place. So if you want greater control into inspection of each and every step, then Agisoft is also very good software for that. Then this is the orthomap that we get after processing using Agisoft Metashape. So although all softwares have an option for report generation, commercial softwares provide more polished survey report that can be useful for understanding the calibration, accuracy, and the summary reports that are generated with these softwares. They can be directly shared with the end user. So this is one sort of report which is generated by the Agisoft Metashape software. So first of all, it is showing the survey area. It is showing 634 images which were used for collecting or generate in this survey area. It is also showing the number of overlaps here. So you can see, except for this small point here, all images have 9 or more than 9 overlapping images, and this few points here we can see they have maybe 7 or 8 overlapping images, but all points have more than 2, which is the bare minimum number of images we need, overlapping images we need for generating the height information. Then in the report also we can see the flying altitude, we can see the ground resolution per pixel, we can see the coverage area, we can see the camera stations, the number of tie points, which is another word for key points. So number of matching key points is 7,53,000. Then the reprojection error is 1.46 pixel. So ground resolution is around 2.5 centimeter per pixel and reprojection error is about 1.5 pixels. And the camera model that was used to generate this data set is given here. Then it has a dedicated section on camera calibration where it shows the distortions, radial and tangential distortions in the camera lens. So we can see the radial and radial as well as the tangential distortions in the lens, and whatever coefficients has been found by the software with the help of camera calibration. So the focal length in pixel was found to be 4046. The location of principal points was found to be Cx and Cy as given here. Then also tangential and radial camera calibration coefficients are specified here. In addition, it also provides information about the camera locations and the error estimates. So here we can see that locations which have more error estimate, they show in reddish and orangish colors, while locations which have smaller errors, they show in the greenish colors over here. So ultimately the error in x direction was found to be 3.2 meters in the camera location. Error in the y direction was found to be about 2.0 meter, and error in the z direction was found to be 1.5 meter. So this shows the camera location and error estimates. After that, it also summarizes all the processing parameters which are given by the engineer in generating the digital surface model and the orthomosaic map. So important parameters can be what was the system setup for processing the data, what was the processing time, what was the memory usage, also again the number of images that was used, what is the coordinate system that was used, information about the tie points, information about the alignment parameters that were given by the users, information about the model that was specified by the user, and also in the end the orthomosaic was received. Then what was the size of the orthomosaic, what was the resolution, and what was the overall the storage size required by the orthomosaic. So in summary, when we talk about the cost benefit, interoperability and scalability of the different software, it boils down to, first of all, that commercial softwares, they have high initial and subscriptions cost. So they may save partially on survey labor with fast, accurate processing and dedicated support. On the other hand, open source softwares, they have free or minimal initial cost and they save almost 100% with respect to the commercial softwares, and they're ideal for budget projects, but then they require technical expertise also. Then in terms of the workflow interoperability, commercial softwares, they support GeoTIFF, .las, .obj, and they integrate with GIS and CAD. They also provide APIs for automation, and they may have some proprietary format limitation. For example, the commercial software may have some specific formats which are only applicable for that particular company or for that softwares provided under that particular enterprise. On the other hand, open source softwares, they provide very open workflow interoperability. So they support all the open formats, .geotiff, .las, .obj, and they also give strong GIS integration as well as customizable API, and they avoid locking in into a particular software. So you have more option and you're more open to try out different softwares in open source. In terms of the format, commercial softwares, they process again JPG, TIFF or DNG formats. They output GeoTIFF and .las, .obj multispectral formats. And open source, they also have they also support similar formats, except that commercial softwares may sometime have their own logged in formats. In that case only they become different from open source formats. In terms of the GPU requirements, commercial softwares, they support CUDA, They also support open computing language, and combined with this setup, they provide 2 to 5 times speed up in alignment and densification and meshing. Open source softwares maybe sometimes maybe slightly bit less efficient than commercial software, but if you're doing it for your academic purpose or research purpose or don't have particularly a very large area, then I think efficiency or speed of commercial and open source software is quite similar. In terms of supporting cluster and cloud, commercial softwares, they are supporting cloud platforms for scalable remote processing. For example, you can upload your data into the cloud, and even if you don't have your own GPU or your own very powerful desktop setup in the field, you can still get the results in near real time using the commercial software. On the open source software, even though there is no such support of the cloud, we can still set up a cluster, or we can still set up them on a server for distributed processing. So they are also compatible with AWS and GCP cloud scaling. So in summary, we have learned today that there are three major stages in drone survey, starting from data collection using flight planning, data pre-processing, which is more focused on geotagging, and data processing, which is for DSMs and orthomosaic generation. We also learned about free and open source software, which are suitable for academic learning and research, as well as about commercial softwares, which are suitable for professional projects. So thank you very much.